Today's lesson is gonna happen in this one file called code.cs. We have a classic program still with a main method that entries into nothing, just so this tool here doesn't complain about missing main methods, but it's all gonna be very theoretical, nothing we can actually run. Or is it? We'll see later. Also, bad news, still can't get the tablet to connect, so yeah, I did spend about an hour trying to debug that thing. Let's not call it names. Good thing I have plenty of experience with debugging things. None of that helped me. Did find a couple of issues, but none of them were the only issue, and I don't know what to do anymore. Gonna have to actually contact support, I think. Ugh. I'm sorry for those guys. Anyway, today's lesson is gonna dip us a bit more into the larger differentiating factor that keeps certain languages in specific categories. In case of C#, that category is object-oriented language. And we're gonna just dip slightly into it. We're not gonna get knee-deep in there. But I think this is gonna be a good start. Well, let's set the scene. Let's say we're having a game which has a couple of players. So of course we have the class player, right? Which isn't gonna do anything for now, just to write it down. And our players can move around in a level, so we need a level. And we're gonna keep that empty as well for now. And then lastly, players need to do something in that level. They need to be able to interact with things. So for example, we're gonna have something called chests with sweet, sweet loot inside. That means our level needs to store chests, or maybe several chests. Let's just do it the very simple way. Like chest, like an array of chests. So our level has a couple of chests, and a chest has a method that lets us open it. And actually, let's add some code. Put a using up top, using system. Gonna use that a bit more than console right line. Not gonna play any sound. Yeah, just opening the chest. And the player can now have a method for open chest, which gives them a chest, and then they can go chest.open, and voila, player is opening a chest. Again, this is very rough structure. We're not actually gonna program a working game or anything. So just to be clear, I just can't find any better examples for this stuff than video game, because kind of feels on topic. Anyway, that would be our first interactable. Now, let's say we're gonna expand this a bit. What if we have other things the player can interact with? Maybe public class closet. And the closet can also be opened. I mean, it's functionally very similar to the chest. It's just slightly different in a couple of ways. Maybe there are things you can do with a closet that you can't do with a chest. Chest might be able to be pulled around. Closet might be very much in place, but the closet might be bigger, so there's more loot, and maybe the player can hide in there. Well, let's say for now also just a method for opening. Let's copy this because I'm a programmer and we're lazy. And why write it twice? Opening closet. And actually let's copy this one more time because maybe in that level we find some hidden books. That you can also open. Also, of course, need to store that in my level. And we have the closet. Closets, and we have a couple of books that all might be part of the level. Whoop, that was too much. Scroll back up, please. And now the player needs, of course, some methods to interact with that stuff. So we have a closet. That. And let's copy this just once. Open. We can use that. Book. Book. Book that opens. So, like that. Our player can open chests and closets and books, which are all part of the level, and which all do different things. Alright, seems fine. Though it's a bit annoying that we have to write so much. I mean, it makes sense that I have to define what those are, to a degree. Okay, but I have to write them all down separately in the level in here. I have to write several different methods in player for each one, and they all do basically the same. I mean, maybe one thing I can change. I don't need to specifically put the name in here, I can just call it open. Since the signature is still different, we have different types in here, different data types, we can leave the name the same. Right, keep in mind, signature of a method needs to be unique, but the signature includes the return type and the parameter types. So the same name is fine. Maybe this is a bit more consistent. And it's a bit easier to copy paste now. Still annoying, because, well, now I have to add another one maybe, because the player might want to leave the level, go to another one. And for that we might need a door. The door also will have, every time, scrolling down, was on 20. We also have a method called open, opening door. Which is great, because now I have to copy paste that. Door. Doors. And to add open. Opening door. So, quite a bit of work, just so we have the concept of a door that we can open. But all the work was just copy pasting. It's not like we did anything new in here or in here. It was basically the same as all the other interactables, just the class itself was different. But all the rest is copy paste with just a different data type. And there are two major ways we can work a bit around this. About this. Doing the same thing again, but with different data types. And one we're not going to talk for a while, but the other involves the object-oriented part. See, for us, it's pretty clear that we have different interactable objects that all have basically the same way we interact with them. I mean, it's always just, we call the open method. We always open the thing. It's pretty clear to us. But to the computer, these names have no meaning. The computer just sees this is one method in one class. This is another entirely different method in a different class, which is kind of true. It's a different method. But the way they're used is so very similar. The way all these classes are used is so very similar to one another that as far as the logic goes, we just take a thing and open it. Doesn't matter if it's chest, closet, book, door, whatever. Just take a thing and open it. Same with the levels. We can put them out like this individually. Like I have a list of chests and closets and books and doors, but actually all we care about is we have them stored somewhere. Just store a list of things in that level. Why make it so complicated? And the easiest way to do this, at least as far as understanding goes, and actually, no, I think it is the easiest one, would be using a so-called interface. Interfaces are a way for you to label a data type as something more generic than it actually is. What do I mean by that? Actually, before I do that, maybe let's iterate on that a bit more. As I mentioned, for us, from a logical standpoint, all these things, all these different interactable items or objects, whatever, can be opened. Are all things that a player can take and open. And sure, the specifics of how that works, how does the opening affect the object and the player and the world, that's different for each one of them. So having its own method makes sense. But all these methods would be called the same, would be used the same way. In every case, we just call open. That's it. And all the specific stuff that has to be different for each one happens inside that method, but not when we call it. So if we just break it down to we have a thing that can be opened, and that's it. Then we could apply the same logic to all these types. This is a thing that can be opened. This is a thing that can be opened. This is a thing that can be opened. This is also a thing that can be opened, kind of. Not really a thing, right? I mean, walk-in closet would also not be a thing. Semantics. In any case, all those are things that the player can interact with by opening them. And the level itself also doesn't really care about this is a chest or a closet. It just cares about I have a thing the player can interact with. That's even more broad. It doesn't need to be a thing that can be opened, it's just a thing. That's it. So we can define this abstract category of thing that can be opened, or just in general a thing, and have the player and the level just work with that abstract understanding of thing that can be opened. But leave the specific classes down here as they are, with individual methods that behave differently. And to do that, we're gonna introduce an interface. And it's gonna look very similar to a custom type. So usually I would make a class maybe in here or a struct, but now I'm calling it interface, which is another keyword. And traditionally interfaces, the names always start with a capital I, which is, for one, I, because it's an interface, so that's easy to remember, but I always think of it as I am something. Just hint a bit at the normal English way you could rephrase something. So in this case, I will call it I can be opened. Now, you don't have to be fancy with the names. In the end, it's just a name, but I kind of like to do it this way. Because this will now apply a general rule to data types we define. Well, we're gonna apply this general rule to data types. And that's gonna tell us that this data type later is something that can be opened. And for now, this is just empty interface, nothing in here, which can actually have uses, but we want to make it a bit more useful for our case, and we're gonna provide it with a method. The open method, the one that all our things have in common. Something weird happens here, however. I'm putting down a semicolon. I'm not adding curly brackets. Only the semicolon. Because we're not actually writing code here. We are now far away from any actual execution of code, of actual instructions for the computer to do. This is purely to tell the computer that something is something else, purely defining something. Abstraction. And so we don't need to add any code, we just need to tell the compiler that yes, we're done, this is one method. That's it. Also, notice how, unlike in every other case, I didn't add a public in front. I didn't use to in the past, but since we introduced the different accessors, I always try to add them, because the defaults are not always obvious. For interfaces, however, I couldn't add one. I could write it down, but this would not compile. Actually, we can try that. I'll tell you, that's not valid. Because, again, this is not actual code. This is just a definition for a thing. Well, hello, Checkham. And as such, it doesn't need to specify who can see this code. There is no code someone could see or not see. The code that someone sees is down here, where we actually have code. And so here the accessors are important. But up here, they have no relevance. And this is the full interface already. We just have, similar to a class, a keyword specifically to define an interface. We have a name that usually starts with an I, but doesn't need to be. We can do it this way, compiles perfectly fine. It's just a convention again, like uppercase for classes and lowercase for variables and all that. And this is actually one of the conventions that's very standardized, that basically everyone uses. There are conventions that are more a matter of taste. But you should try to keep that in the traditional style with an I in front. Now, how do we use this? This is gonna look a bit weird. People usually call these blueprints defining a structure, not on usage. Okay. Guess we have someone in chat who actually knows this stuff, unlike me. Well, welcome. You can backseat me a bit and correct me where I'm wrong, so... This is now a blueprint. Going back to how we use this interface. After defining what we are creating, class in this case, and giving it a name, we're now adding colon behind. And this colon has the function of telling the compiler that we are now adding additional information about this class that are not about the way we use this class later. Well, not directly. This is all just additional information that define how this class is going to work, that are mostly used for the compiler to give it a more narrow range of how we use it or plan to use it. Which lets us then do things we wouldn't be able to do otherwise, because the compiler wouldn't be sure what our intentions are. And right now all we want to do is can open things? Can be opened. Okay, can't remember. Can be opened. That's it. This class is called chest, and it is a thing that can be opened. It implements the interface can be opened. Essentially, by adding this little colon and the I can be opened behind the class name, the compiler now forces us to add a method called open. It doesn't return anything and doesn't get anything in this class. If I just leave that out, let's call it open too, we will get an error. Because we told the compiler this class is something that can be opened. And now we get the advantage that we can use that method on that class as just general, this is a thing that can be opened. But that also means the compiler forces us to add the method. We can't just say, hey, this can be opened, but then not offer the methods to do so. And we do the same down here. I can be opened. I can be opened. And purely by coincidence, of course, I have already a method called open in every single one of them. Can be open. Let's see if we can compile. No errors. So all of these are now recognized by the compiler as a thing that can be opened. And now we can do something cool. Well, this is not a class. You can't create a new I can be opened. This is purely information. This is just fluff for the compiler, so it has a better understanding of how we use our code. It holds us to certain standards, certainly. We have to add the method, but it also lets us get away with a few things. But just because we can create an object of type I can be opened doesn't mean we can't use it as a type. What we can do is write a method called open that gets an I can be opened. As if it was a custom data type we wrote, as if it was a class or a struct or whatever else we used. No different from that. And in fact, I can be opened as a method. Yep. Called open. As is defined up here. We have an object of type I can be opened. And we know it has a method I can be opened. Objects have a method called open. So the compiler is fine with using this code because it knows for sure it will have a method called open. We can drop all of these now. All the player gets is a thing that can be opened. It opens it. And the same way, and we can use it as well in here. And be opened. I can be opened. Let's actually make it a bit easier. Sounds weird otherwise. We can use it as a type, but we're not able to create it. Let's actually go into the main program and just see the difference. I can create a door just fine, no problem. I cannot create a and just use an I. Because again, this is just a definition. This is not some, or more, not actually a definition itself. This is just additional information about other things. This is adding information to something larger than itself. This is just, I have a method called open. This is not, I am a data type that sits in the heap, that has the ability to store data. No, this is just, hey, I have a method called open. It cannot stand on its own. So if I compile this, get this. Doesn't work. So to use this, I can just do this, for example. Actually, we can do it further. Don't even have to store it before. I can do this. This might throw people off, maybe. Because so far, I create something on the right, and I store it on the left. And what I have on the right needs to match what I have on the left. Exception would be something that can be implicitly cast. Because I can store an integer and a long just fine. But we saw a couple of times already, I can't just store a double in an integer. Or a string in an integer. And for our custom data types, we always had to match on the right what we had on the left. So let's say we have a player now. Whoop, player key, continue player. And we can just do that classic style. We can now call play.open and P gets our eye. The eye can be opened. Which secretly is a door, but as far as the compiler is concerned, no, this is just a thing that can be opened. Can also do a book in here now. Or a chest. Works just fine. Of course, if I go back to the just directly a chest, this works too. Now I wish I had the tablet working. As mentioned, still haven't got that thing to run, so I can't really draw that out. Otherwise I would have shown you the tables. Well, I have to write this out in here, I guess. So type name. Think back to our tables that we had initially. Actually, this looks not good. Maybe like this. Ah, well, will do. So before we would have chests, I, and then the mystery address to the heap where we had the data stored. But if we do it this way, I can be opened. Well, this is what we have in there. Okay, let's move this out a bit maybe. And it still refers to the same address as the chest. Actually, let's make it C equals chest. That like that. 1, 2, 3. Just something, for example. So both of these use the same address in heap, and in the heap we would actually have the instance of the chest, the actual data. Remember the episode about the heap. What I left out back then was that the data at this address does not only contain what we have stored in the instance itself. In this case, the chest doesn't really have any fields that can store data. So you might think it's just an empty address without anything, but I left out that there's some meta information for the language itself that you don't use directly. Maybe well, you do use it in a way directly, but you're not aware that you're using it. So basically in the heap, we don't only have data for, no, yeah, let's use data for class, like that. We also have data about object. So in this address, we still have all the data we stored in there, seen in previous episodes. But for the computer, there's a special section about the object itself, containing information about what it is, and what it can do, and what it cannot do. And while up here, we are kind of constrained to the data type we stored on the stack in our little table, the computer can do more if it's necessary. It gets a bit weird. Actually, once you start playing around with the different ways you can store data and how you can name it and define it, there are some really, really weird constructs you can create in C# just from the basic rules of, hey, I can take a C, a chest, and store it in I can be opened, and I can still use it as a chest, despite being not a chest anymore. So on the stack, this is what we have. On the heap, this is what we have. So when I go to the method open, all I need is something that can be opened. It needs to just fulfill the criteria for it has this interface, which a chest has. So we can call this method, and it will call the method open, which has to be in there, otherwise we wouldn't have been able to compile the chest. So yeah, the method is here, we call it, it runs just fine. But what actually happens is that when we call this method open, the computer will first figure out what type of object is it actually. Because I can be opened is just the interface. It doesn't have any code the computer would be able to execute. There is no assembly stored for open in I can be opened. And so to actually run further code, it will need to figure out where do I go from here. And this method is stored in another object that is defined on the heap. It's part of the meta information in our object. So while this is a I can be opened, the compiler in the background knows that actually this is a chest. And I will call it in chest and not in I can be opened. Does that make sense? And this is a very important step in general for object orientation. This matter of what I write is not necessarily what happens. I'm just giving vague instructions, and the computer has a way to figure out what to actually do. Again, I can be opened doesn't have code to execute, and yet I can tell it to do something. That only works because the computer in the background is doing some actual work, figuring out what the heck our I can be opened actually is. Because I know, and the computer knows, I can be opened doesn't exist. It's not a thing. It's just additional information about a thing, but not a thing in itself. And because we can have the computer figure it out on its own, we are allowed to store the full chest as something else. That means, however, we lose some other figures. Well, let's actually use push. Push sounds nice. String chest. this chest has a method open and a method push. And if I'm in the program, I can call c.push just fine. Still can't get used to the missing of key combinations. Okay, let's... Probably not. Nope. Can I... Okay, that I can do. Cool. At least that works. So if I compile this, pushing chest, opening chest, everything works as expected. If I were to try to now do I.push, would have an issue. Why is that? After all, I just told you, if the computer tries to open our I can be opened, it will just look up what is it actually, and then call that method for that class. And here I am calling I can be opened dot push. Shouldn't the compiler be in, or the computer during runtime be able to figure out what's going on? Like I'm calling push, it sees, oh, it's a chest, and it's calling push on the chest. The answer is yes, it could probably do that, but that would make a lot of things a lot more complex. And writing compilers and languages is hard once they grow to a certain size. I mean, it's hard in general, but once they're the size of C#, things like that can have serious knock-on effects. And the immediate problem we have with this is, if I have door D, right, and I know can just store our door in I. Okay, let's put it down there, do it like this. This works still just fine. I can just say, hey, this is an I can be opened, door can be opened, I stored an I, and I can still open it just fine, because that's definitely defined in the door. But door doesn't have a method called push. So this cannot work. We're actually trying to call the method push on a door, but we haven't defined such a method. Okay, let's say we did define the method. Let's go a step further. I mean, doors in general can be pushed. Why not do that? Just complete. Pushing door. So now we have a method called push that we can call. Right, right. But what if this isn't a door? What if this is a closet? You see where I'm going? The issue is that I can be opened can be more than just a chest and a door, things that do have a push method. It can also be other things that do not have a push method. All that I can be opened guaranteed us was that we have a method called open. If I want to call a method push on an I can be opened, on a thing that can be opened, I have to extend the interface to also include that, yes, this can be pushed. I have to add that in here. Now this would be perfectly fine. Now we can call this. Of course, now also we have the issue that the compiler will not allow us to name closet and booked and I can be opened, because now they don't have a push method. And I forgot to add the... Oh, what did I miss? Oh. Whoops. Never mind. Okay. Now we have the issue that if we do say that I can be opened includes a push method, we have to ensure that all the classes that we mark down as I can be opened have a push method that can be called. We told the compiler this can be opened with an open method, and we also told the compiler that it can be pushed. But this cannot be pushed. This can't either. That's where we have an error. And that's also not what the interface is for. So we remove that again. All of these objects only have in common that they can be opened. So these abstractions make things more general, but you can also think of it as finding the least common denominator of several different types. They have several overlaps, like chests and doors can push both just fine. I can open both. But the only thing all four have in common that I can open them. So the interface that applies to all four types can only include open. I can do a second interface though. Interface I can be pushed. Let's keep the same naming style. Like this. And a chest can be pushed as well as opened. And I do that by just adding it with a comma. Now it's an I can be opened and an I can be pushed. And so is a door. The compiler should not complain about this anymore. Except I can be opened. Doesn't work anymore here. I need to have an I can be pushed. And on that, I can call push. Just fine. Because if I now try to do something like new closet, try to add that, that will not work anymore. The closet is something that can be opened. I can store it in I just fine. But a closet cannot be pushed, so I cannot store it in the... I cannot store it with the label of I can be pushed. And you see familiar message cannot convert. Because it doesn't find a way to match the requirements for I can be pushed with a closet. I can be pushed needs to have a method called push. Closet doesn't have a method called push. This doesn't work out. It's violating the rules. So, we have to remove that. Works fine with the door, works fine with the chest. Not with something that doesn't officially have a push, an enforced method called push. Alright, let's leave that apart for now. Now I have a couple of things that all can be opened in the level. But how would I find something that can be opened? That is a chest. For example, if I just want to get the different chests in the level. For now, all we've done is always bring something to a more general outlook. We've always tried so far to make something very specific, the chest, the door, something more general by using the interface. We always start in something more general and then executed that as something more general, abstract. But if I want to something specific, public void, public, let's do it this way, public C count chests. Something simple. We just want to know how many chests are in this room. To figure that out, we have to be able to see what each thing in here actually is. So we have to kind of make use of this information. For now, let's just iterate through the array. 0 less than length and plus I, like this. And to get to an individual thing, do this. And actually, let's make this a bit easier. And like this. That can be opened thing. I want to know if this thing is a chest, a door, closet, or a book. There are two ways I might accomplish this. Well, technically more, but for now let's focus on two specific ones. The first one is a very direct question to the computer: what is this? And to do that, I can use one of the very common, as in the sense of every object has it, methods. Just like the toString we talked about last time, every object we create, everything, has this method called getType, which literally gives you the type of what it actually is. It reads basically the information that is stored in the meta information on our instance. And what we get in return is a class called type, fittingly. This is another data type that contains a bunch of additional information. There are lots of fields and additional methods and a lot of trickery that you can get in this special type that comes in the system. But we don't really care about the details in there yet. I mean, you can, if you just want to test something, you can just go type.toString and you get plenty of information for yourself for debugging, just to know what actually is it. We want to check, however, if it is a very specific type. And to do that, we can use another special keyword called typeOf. And typeOf is a rather unique type of keyword. Well, not so unique, but it's in a special class of its own, because this is not just a keyword, it's also a method, function. We add brackets and we add something in these brackets, and that belongs all together in one block. What we put in typeOf is the type of a class, or the name of a class, a type, an actual class name or struct name or some kind of type name that the computer can identify. And this typeOf will tell the computer to give us a rundown of what this type is in form of another type instance. Type of thing, or this type of chests. And now we can just compare if type of thing is the same of type of chest. And we can do stuff in here. So let's make a counter, and counter, well, it's 0. If that is equal, if that thing we're looking at is a chest, then counter plus plus. Increase the counter. And if it isn't, we don't. And actually, let's remove the brackets. Like that. Now, this works, but I prefer to put this outside, because this call here, this little keyword type of chest, that actually does take some resources, because it has to be, this is something that has to be checked during the runtime, when the computer is actually running. You might think the computer already knows what a chest is, so it should be able to fill this data when I compile already. But that's not how it works. This is gonna be called at runtime every time you use typeOf. And if I use it in the loop here, it will call the same underlying methods several times. And that's just a waste of resources. So I put that out here, put that in here, and then we can return counter, and we know how many chests there are. Let's see if that compiles. Compiles. Now let's do something interesting. We're creating a new level. And this level now thinks, what's new? things. We're gonna use the classic way for now still. Let's use 5 things in that level, right? And you know what? Maybe it's time to show you some shortcuts because I'm too lazy. When we create a new array, we can actually pass on the values directly. So instead of writing out how many objects I have in there, I can just add curly brackets and just write them comma separated in here. So I can say new door should have 1 door at least, so that I can get in and out, and maybe 1 closet. And there's chest on one side. And here there are 2 chests. There's another closet. And in that closet, we might, or next to the closet, we might find a book. And maybe there's another chest in the end. Now this is our level, and let's try to count, what did I call the method? Count chests. Chests. And then we can console and dot right. Line, let's do it this way. Like this. Let's compile and run. Ooh, what happened here? Ah, obvious mistake. Things as an eye can be opened. And I forgot to add the system using in here as well. What I did add it in this file, and it's the same program, I did not add it to this file. These usings only apply in the file you define them in, and these are 2 different files. Okay, does it compile now? And there are 3 chests in the level. That's correct. And let's move it out and try again. And now there should be 2 chests. Perfect. So our code works. What is the other way we can do this? Well, this is a very direct question of, computer, tell me what that thing actually is, and then I'm comparing that detailed information with some other detailed information I have, and I do that myself, and then I come to the decision that is that thing. There's an alternative. What if we don't do that ourselves and just let the computer do it for us? Because it's a pretty easy question, right? Is that this thing? Is thing chest? Yes, it is, apparently, in 3 cases. Let's do this in a door. Only 2 chests. What I did here is part of a larger chapter called pattern matching. And it's a rather useful tool, but it has a lot of, especially in the newer versions, there are a lot of things you can do with a lot of special syntax that I'm not gonna get into for a while. But this is one of the very basic usages, and I just wanted you to see that it exists. So it's doing exactly the same as we did before. Okay, so it's doing all that, I see. It just checks what type is thing, what is chest, and the type of thing the same. Then this whole statement becomes true. So all of what we did by hand is now done automatically in the background. You don't have to think about it, which makes it very useful for writing code like this, right? So since we don't need to make it so obvious anymore, You can also simplify it like this. Oh, not. What did I miss? Okay, maybe not. Let's ignore that for now. Let's pretend that never happened. Nothing happened. Let's see what that is. There's more you can do though. To show pattern matching is more useful than just to see if it is something else. It can also at the same time just give you a variable that is a chest. Basically, I'm declaring a variable, and if this is a true, if thing is a chest, then store the chest in the variable C. If it is not a chest, then don't store it in C. And what that means, I can now do C.push, for example, which I cannot do on thing, because thing is I can be opened, it doesn't have a push method. Chest has a push method, specifically chest, so this code works. Pushing the chest twice because there are two chests. This is pretty useful in a lot of cases. What would be the alternative? Now, let's say I don't want to use this feature. What I would have to do is just clear the variable down here, just C, and I want to assign it the value of thing. Well, this will not work because thing isn't a chest. It could be anything, and the computer will complain about it, as usual. And what we can do here is the same we do in any other case as well. We just convert or cast. And in this case, we can directly cast. Because we know thing is a chest. We know for sure. So we know that the computer can interpret this thing as a chest. So we just run it as such. If you're wondering, if I do the same thing outside and run the code now, it would of course try to convert everything into a chest. Which cannot work, because not everything is a chest. So what do you think happens if I press run now? 3, 2, 1, boom. Our old friend, the unhandled exception, is back. Because this can be compiled just fine. It's valid code, the compiler accepts it as, okay, you are explicitly telling me to treat this thing as a chest, and I will just do so. I will do exactly that. And then during runtime, it notices that, yeah, I tried to treat this thing as a chest, but it wasn't a chest, so I don't know what to do anymore. And since we didn't add any exception handlers, unhandled exception, the entire process crashed. So out here, bad idea. In here, just fine, because in here we have already made sure that it has to be a chest. And instead of writing this out by hand, we can also just have it declared in here, and because of pattern matching, it will be filled on its own. And it's just fine. Because if we just count it, we don't need to declare a variable, and we just have it compare it to the class. We can also do it another way. We can also do door, of course, which now gives us the wrong data because we wanted to count chests, not doors. But the result is still correct. There's one door now. And yes, that is interfaces. And I mentioned earlier that very beginning, empty interface can have its uses. Well, let me show you something else we can do. One last trick. I am thing. And we leave it empty. And we can take now every single one of these. Just add I am thing. can add them to here as well. What I do in here now is I am thing. Oh, that's wrong. I didn't want to save. Like that. Our program. Change it like this. It still works. It's just not too useful because we can't really do anything with a thing. Just because it's a thing doesn't mean we have the methods open or push. Even though everything has an open, we haven't defined the method open, but we haven't declared it inside the interface IamThing. So this is purely a token we attribute to the different classes. Just to mark it down as something that exists. We can make it slightly more interesting by actually adding this. What we did here is the same in classes. We told the system, the computer, that I can be opened is a thing. We can do the same here. I am things. It's also additional information for I can be pushed. And actually we can do a bit more. We can go I can be opened is also attributed to every I can be pushed, which currently matches our code. So far everything can be opened, and some of that which can be opened can be pushed. So this is valid. And that means we can actually remove some things. We know an I can be opened qualifies as I am things. So if I already say I can be opened, I don't need to specifically tell it that I am a thing. It already is determined that I have to be something that is a thing, because I can be opened, and I can be opened is a thing. And we can do that here as well. I can be opened already includes the thing, and I can be pushed includes I can be opened. Thing doesn't need to be specifically that. We can leave it in there, like I can compile this, or should be able to compile this. And things. Oh. It's better. Compile this just fine, but this is unnecessary because it's already implied through I can be opened, and the same way I can be opened is already implied through I can be pushed. So it's just unnecessary, doesn't matter if I add it or not. So I am a thing. All of these are things. Some of these are, or actually right now all the things that are marked down as I am thing are also I can be opened. And some of them can also be pushed. And that's the magic of interfaces. You can just freely combine them and create these abstract structures. Think of it a bit like categories. Like you categorize this chest as something that can be pushed or can be opened or as a thing. And these categories can themselves be categorized in something larger. We can also switch this a bit around and say this is both I am thing, but they are separate from each other. So I can be pushed and I have to put them down separately in here now. Because both I can be opened and I can be pushed say I am thing. In terms of hierarchy, they both are following under I am thing. If you imagine a tree starting with I am thing that splits off into I can be opened and I can be pushed. These two are siblings in our hierarchy. Before we had I am thing, I can be opened, and I can be pushed in a linear hierarchy downwards, 3 levels. But now we have only 2 levels, I am thing at the top, and I can be opened, and I can be pushed on the second level below, and they are separate from each other. They're siblings, but they are separate things. can also be done. So think of a bit like categories maybe for your custom types that you define that allow you to define behavior in terms of methods that they are guaranteed to have. And that allows you to mix different data types that work differently from each other, but share some commonality between them. Like all of these share some features with each other that can all be used in the same way, even if they have different outcomes. And so you categorize them as this one shared thing. And that makes your code a lot easier. Honestly, that's it already. I didn't want to do any more today. Doing more would be pushing it. But that's your first introduction into the world of object orientation. This is a very important concept. Not just interfaces, but the whole idea of a chest is something that can be pushed. It is something that can be opened. It is a thing. But it's still separate from other things like closet. Right? The whole hierarchy, the whole idea of these are very abstract things. Very abstract definitions that don't affect your code directly. They just affect how your computer understands the code. And the way you communicate to the computer what your code is supposed to do. Right? Pure abstraction. No code anymore. Extremely useful. Now then, since that topic is done, let's quickly remove this, clear up a bit. I believe last time I gave you some homework, and since we have a bit of time, let's maybe try to create a method like that on our own. I don't have it on the site, so I don't know what it was exactly. I think it should have looked like something like this. Static. I think it was a parse method, right? Try static int parse string input, something like that. And int equals parse like that. Like that. Alright, I gave you some simplifications. You're able to assume that this number is gonna be an integer number in the positive range, so no plus or minus in front, and it's all just gonna be numbers, at least on the simplest way. And the way we are gonna handle this now is I'm gonna start with a variable. Let's throw out value, which starts at 0. Then for it's 0. We're gonna now process the different symbols in our string one by one. And we're starting at the very first one, which is also the highest value symbol. Keep in mind, this is the hundreds, this is the tenths, this is the ones. So we're starting with the highest value, which is the first character in the string, the first character in the array of characters that is a string. Equal I less than input dot length plus I, like that. And to figure out what value we actually have, let's do it like this. We're gonna take the input character at the current position, I, and then we're gonna subtract the value for the character 0. 0 to 9, the different symbols, the individual characters, are all in one sequence. So 0 is going to have the lowest value, and 9 is going to be the highest. And they are not starting at the value of 0, they're higher up. What is it? Was it 48? I think it was 48, right? Or was that for the ABC? Doesn't matter. Anyway, they are in sequence directly next to each other also. So whatever this is going to be, maybe 48, it's going to be subtracted from this value, which is either going to be 48 for a 0 or 49 for a 1. And that's what we're going to put into this integer. So just to give us, for this one character, an actual integer value we can calculate with. And what we're doing now is making sure that every character has a different weight in the total number. And the simplest way to do that is multiplying our current value by 10 and then adding our character value. Like this. So for the very first number, of course, this is not going to do anything. 0 times 10 is 0. But then it will going to find the character value is 1 and add it. So our value is now 1. The next iteration, we're hitting the 2. So first, we're finding out that it's a 2. So we store that as a 2. Then we're multiplying our current value, which is 1 at that point. So we get 10. And we're adding 2, so we get 12. Third iteration, we're getting a 3, multiplying our 12 by 10, we get 120, and add our character value 3, we get 123. Return 3. Return value. This. And if I didn't make a mistake with the casting, it should work. Ta-da! Very simple parsing. Now we can go a bit further. We can make some checks. If this is some of the bonus start. Input I. If it is less than the value of that, or 0. Or if input I is greater than a 9. So if it's not an actual digit, let's just make a general exception. Valid character input like that. So code should still work just fine. But if we include something that's not valid, we get the exception invalid character A. Maybe let's add some quotation marks around it. Looks a bit better in the output. So we have that. And then we can do one last thing. If input and okay, there are a couple of ways. Let's do it the stupid way. If I equals let's mix it in here. Let's mix it in here. So one exception for this is of course the very first character, which could be a plus or minus. Again, that's just bonus now, but let's say it is. If I equals 0, so only the very first character is going to be checked. If I equals 0. And input I equals plus, or input I equals minus, which we gonna combine in brackets because it has to be this and either of these. If I didn't add the brackets, it would just say if it is I equals 0 and it's a plus, or if it's just a minus, regardless of the value of I. So if it's this case, then we can just continue, which is a special keyword, which I don't believe we have talked about before, that lets you skip the rest of your current loop. So this keyword, continue, always references the nearest loop, so to speak. And that would be this for loop right here. Sorry, to clean up a bit. Yeah, and what this does is just say, hey, skip all the rest down here, just go back to the top and try the next iteration. Just pretend as if this is the end of the loop. So we skip this exception down here and we skip all this evaluation down here, just fine. And this is the only exception we have. Of course, this now leaves us with one last step. If it is a minus, we're actually generating a negative value. So we should store that as well. Bool is negative. We start out with the assumption that it's not negative. And it's either one. Let's just make it simple. Let's input I minus, like that. And at this point, it might be better. Char C equals input. Just to clean up a bit, instead of input I everywhere, we just use C for character. Character. That, and here as well. There as well. So in theory, you can just do it this way. And let's put it down here as negative, then minus value, otherwise value. I hope you remember the trinary operation, which is basically an if, then this, true, and a false, then this. Right? Question mark to separate the condition, the if part basically, from the first closed bracket if it's true, and the else part is then separated off by the colon. It's been a while, I know, but for cases like this, very useful tool. Let's see if we can get a negative value. That works just fine, and if I make this a positive value, it should be just 1, 2, 3. Of course, this is a bit convoluted. For example, why do all these checks if it's not the first? So instead of doing this inside the loop, it might be better to do this outside of the loop before we start looping at all. And then start the loop, if necessary, on the second character at index 1. But that's optimization, we're not talking about that, and I'm too lazy to write that down now. It works, right? But yeah, that's a very simple way to handle this parsing. Oh, and naturally, you can turn this into a try parse by simply replacing this throwing exception with a return false, right? Can at any point just return negative result as a not negative number, as a negative, it's not a number, we can parse it without the exception. So much for the homework. As for new homework, there won't be any. I can't think of any good exercise you can do at home for interfaces right now, because they are so simple. Maybe you can just play around with yourself, but otherwise look forward to the next time, because it's gonna be a doozy. Oh boy, I hope my tablet is working by then. Anyway, thank you for joining in, and see you next time.